One of the things we need to understand is the vernal equinox. So the vernal equinox is the first day of spring. It's March 20th, and it's when the center of the sun is directly above the equator, and we receive about 12 hours of daylight. So the vernal equinox is this reference line here. This is from the sun to the earth. There's a couple of other interesting things going on. So if we look at this diagram, let me see if I can zoom in a little bit. At the vernal equinox, the equatorial plane and the celestial plane intersect, or the ecliptic plane. So this is the equatorial plane is the equator of the Earth, and the ecliptic is the orbit around the sun. So those two intersect. And if you look at this line, the vernal equinox is a reference line that goes this direction to the sun to the first point of Aries. So this is lining up with the constellation Aries. So this is a reference direction. So we would keep the same angle as as the Earth goes around in this orbit. It's always going to be pointing that same direction out into space. It's not going to change. As so the Earth spinning around doesn't have anything to do with it. It's the point. It's this reference line from here to Aries, and as it goes around the orbit, we're going to keep that line parallel at all times. All right, that's kind of a quick explanation of the vernal equinox, and we'll get on with our video. All right, so let's look at this. This is a simulation. Right now in the simulation, we see the equatorial plane. So this plane is, it goes through the equator of the Earth. We see this line here representing the North Pole. So if you took this on down, it would connect to the Earth right here at the North Pole. This is true north, not magnetic north. And then this line is of interest to us. This is our reference line. It's called the vernal equinox, and I explained that a little bit earlier. But this line stays, as the Earth moves around in its orbit, this line stays parallel and pointing the same direction as the vernal equinox. This is, on March 20th, this line goes from the equator of the Earth, intersects the sun, and passes through the sun to line up with the constellation Aries. All right, so we're going to add an orbit. I'm going to adjust a couple of things here. I'm going to turn the eccentricity to 0. You can see we have a circular orbit. And you can see that A is our semi-major axis, so we can change that. And you can see that the higher the number, the further out it goes. And then I'm going to change that one to 0. So we're going to start with this. All right. The first control we have here is a little e. This is eccentricity. Notice as it becomes more eccentric, the shape of the orbit is changing. Okay, so here we would have the Earth at one focus, and the second focus would be right in here somewhere. And this is just helping us understand, is this orbit circular, or the eccentricity of 0, or is it elliptical? So you can see here we have the perigee and the apogee, or the periapsis and the apoapsis. Okay, so the perigee is when it's closest. It also has the highest velocity. The apogee is when it's furthest from the Earth and when it has its lowest velocity. All right. The next concept we need to talk about is inclination. And I'm going to have to rotate it a little bit so you can see this. But right now, the inclination is 0. That means that the plane of this orbit is the same as the equatorial plane. So this satellite would be orbiting exactly around the equator. As we increase the inclination, so let me put it at about 45. We're going to rotate it a bit and zoom out so you can see it. All right, so there you can see the orbit intersects the vernal equinox, and we have an angle right here that's 45 degrees. So notice how this changes. We can go up to about 90. So that would be a polar orbit. Let's kind of look around that. Okay. So that's a 90-degree inclination. Look at this line here. and this would be 50 and then 35, so that's about a 35-degree inclination. So you can see that as we increase inclination, the difference between the equatorial plane and this orbital plane, that's the angle between those two. And notice they intersect the center of the Earth. All right, so all right, for the next thing we're going to look at, we're going to incline this a little bit so it's easier to see. And I'm going to change this value. This is the uppercase omega. This is the right ascension of the ascending node. And what I want you to notice is if we rotate this a little bit, you can see the satellite is right here. This is where the satellite orbits the Earth. So on this side it is ascending, and it's the point at which the satellite pierces the equatorial plane as it ascends. So it's the right ascension. It's ascending over here and it's piercing that orbital plane. If you increase the uppercase omega value, you can see the angle here from the vernal equinox to where that satellite passes through the equatorial plane. So we'll move this further around. So here we go, that's at 142. And you can see the inclination here, and then the right ascension at this point. All right, I'm going to move that down so it's in the first quadrant. We have the vernal equinox here, and it's less than 90 degrees. It's at 50 degrees. So that's where that happens. All right. The next one is, let's do this so we can make sure that this shows. I'm going to increase the eccentricity, and you can see that the perigee is here and the apogee is here. So the next one we're going to look at is the argument of perigee, and it's got some other names too, but this is the point where the satellite is closest to the Earth, and at this time it is from the equatorial plane 0. If we increase this, notice how we now have an angle here, and that's saying that from the point of right ascension, how many degrees along the orbit has it gone? And that's where that perigee occurs. So at this one, it shows that it has a 65 degrees. So starting with 0 here, going up 65 degrees, that's where that satellite is closest. And it can go all the way around. Nope, grab the wrong one. Put that one back. It can go all the way around. Notice how it gets further. So at 180, that would be the opposite side of the right ascension, and then if it's above 180, it's below the equatorial plane. Okay, so you can see how the perigee is moving around the Earth following that orbital plane. So that's the argument of perigee. So far we've talked about the semi-major axis, the eccentricity, the inclination between the orbital plane and the equatorial plane, the argument of perigee, where it's closest to the Earth from that node of that right ascending node, and we've talked about the distance or the angle between the vernal equinox and the right ascension. That's uppercase omega. And now we're going to look at what is called true anomaly. And that is saying, let's put this back at 0 here. So our argument of perigee is on the equatorial plane. The true anomaly value tells you where exactly it is in relationship to that point here that is defined by the other Keplerian elements. So if you look at this, the true anomaly right now is almost opposite the perigee. So that would be around 180 degrees and less than that. So we're just measuring from this point to where the satellite actually is. And again, this can go all the way around the orbit to, it would almost be reaching the starting point, or it would be at the starting point at 360. So the starting point of our orbit is defined by the previous parameters here. Okay, so let's see. What I'll probably do is have you identify some values here, and I'll give you some choices and we'll go from there. So take a few notes about what each one of these means. There's also some diagrams out there online that may help you, but it seems a little easier to explain with this simulation, and I'll also have a link to the simulation. Alright, that's enough for now.